Hello, ladies and gentlemen. Here I'm gonna share about verification techniques. This material was composed by Mr. Yunus, Mrs. Ida, and I, Nanda Alfuadi. Well, we are gonna discuss about this following points about the importance of verifications, pre-processing, and we will discuss about two kind of verification. The first is standard verification method, and then a specific verification type. And in specific verification type, we will divide it, or we will discuss about two main topic. They are methods for spatial forecast and object-oriented methods. Okay, as meteorologists, we know that current NWP has fairly good ability in predicting future atmospheric parameters, but we must remember that NWP model is built based on the physics and mathematics approach, which include some assumptions. These assumptions make model produce errors. We know that. In general, we can divide source of errors in NWP into three elements. Those are initial conditions, model system, and parameterization scheme. The first one, initial conditions, is about assimilation of observational data in the model to build the initial conditions. And the second, the model system consists of basic or governing equations which are used in models. And a parameterization scheme consists of calculating the physical process in a model such as transfer of energy, water vapor, and momentum between atmosphere and surface, like land or oceans, as well as the processes that produce cloud and rain. Because all of these three sources of error is driven by a set of equations, so errors in NWP model actually is systematic error. This systematic error can be identified through verification and can be used as corrections factor of NWP model, or at least as guidance for forecaster to understand characteristic of model. The process in verification carried on to see several objectives, at least 3 points. The first is the best model with the best perform in general. And the second objective is the model characteristic in spatial and temporal. And the last objective is the persistent bias that the model can be adjusted. So, if we are gonna build verification system, these three objectives have to be identified at the end. Well, before we build a verification system, we must know that there are 9 attributes that contribute to the forecast quality. The first is bias. It is about a relationship between forecast and observation data in quantitative data. Skill. It is about the relative accuracy according to some reference forecasts. There is usually an unskilled forecast obtained from a random chance, persistent weather conditions, or climatological conditions. Skill refers to the increase of accuracy value because of models' capability to recognize the data pattern. Sharpness. It is about the tendency of forecast to predict extreme values. To use a counterexample, a forecast of climatology has no sharpness. Associations. It is about the strength of linear relationships between the forecast and observations. Reliability. It is about the average agreement between the forecast values and the observed values. Discriminations. It is about how the forecast can discriminate among the observation data. Accuracy. The agreement degree between forecast output against observation data. It is a little same with reliability and bias and skill is like parameters of verification, and we will discuss in next slide. And then resolutions, the ability of forecast to sequencing or solving a set of events into subsets of a different frequency distributions. The forecast method has a good resolutions if it was able to distinguish different events into different category. And the last is uncertainty. It is about the possibility of event to occur. Well, we have learned about why we need model verification and what kind of attributes which contribute to forecast quality. So it is time to discuss about technical parts. I'm gonna begin with pre-processing. Before we verify model, we must ensure that model data and observation data are the same or homogeneous. At least there are four aspects which have to be homogeneous. The first is area or region or domain. The domain of model that will be verified has to be same with domain of actual data. For example, if we want to verify models performance in Indonesia regions, we have to use observation data in Indonesia also. The second is period. In some cases, it becomes issue that is often forgotten. Period of time between model data and observation data must be the same. If model has variables in daily basis, observation data which is used as verificator has to be in daily basis also. If model is hourly basis or 3-hourly basis, observation data should be in hourly or 3-hourly basis also, and so on. The third is grid resolution. This aspect is important if we want to do quantitative verification. Homogeneous grid resolution is the must because in quantitative verification, both model and observation data will be analyzed in every grid. The fourth is variable unit. We also must ensure that variable unit of model and observation data are same. Meanwhile, the initialization process described as a process in selecting in proper verification technique. How to select verification technique? We will learn or we will discuss about it in next part. Okay, in verification technique, we must learn about how to deal with different data in spatial aspect. There are three approaches that can be used to compare data spatially. The first is single event. The single event approach is commonly used in short-scale verification like daily or perhaps 3 daily and so on. Event is defined as occurrence like precipitation or when element of data or parameters exceeds a threshold, like when temperature is more than 35 degrees Celsius. It is the event. And next is grid to observation. In grid to observation approach, the data that will be verified is grid data. It requires a data extraction process so that it can be compared with observation data, which is point data. If model data is quite rough spatially, require more process to extract data to be more accurate. And the third is grid to grid. The data extract process will be easy to perform with provisions that both the forecast and observation data set have a homogeneous spatial and temporal resolution as well as variable unit. Well, it is about data comparison in spatial aspect. It is about bilinear interpolation. If we want to extract data in one grid or one domain, we want to extract green dot, that is P, or let's say it is model data that we want to verify. The first, we will interpolate the value of this grid in x directions. We will interpolate in x direction between x1 and x2 to get x value. That actually x value also has two values. They are values in y1 and y2. It is calculated using the equations in right side in function of x and y1 and function of x and y2. And the second is interpolating in y direction to obtain the desired estimate. It is about how if we have done the interpolation and we have gotten the uh, value in blue dot, we will interpolate it to get a value in green dot in P point using the equation in point 2 in function of x and y, and we will get the value in green dot. So it is the method, or it is the approach how to get data, especially model data, in not in one grid but in some point in a grid, in a specific grid, because we know that model has a grid that actually it is spatial. It has a width and what is it? It is area, not point. So if we want to make perfect verification, or we want to have perfect data, we must do this technique. And then before we build the verification system, as I mentioned before, we have to know what kind of data that we will verify. Based on data type, there are three type of data: probabilistic, qualitative or worded data, and deterministic and continuous value. Probabilistic, like probability of thunderstorm, ensemble forecast, and so on. The verification technique that can be used in this data type is probabilistic and ensemble method. It, the another method that can be used in this data type is visual method, or we often call it eyeball verification. And the second is qualitative or worded data, like weekly outlook or narrations data, or text-based information. We can use dichotomous method, multi-category method, and visual method to verify this data type. And then for deterministic and continuous value, like KPF or quantitative precipitation forecast, we can use continuous method, spatial method, dichotomous, multi-category, visual, and this is, I think, this is more flexible than other data type if we want to verify this data. And based on spatial and time scale term, we will get the three data. They are in big picture. It is spatial distribution. Spatial distribution consists of time series and pooled space and time. For spatial distribution, we can use all of this method, includes spatial, visual, dichotomous, multi-category, probabilistic, continuous, ensemble method. And for time series data, we can use visual, dichotomous, multi-category, probabilistic, and continuous method. What is time series? It is like monthly average value of something, like SST, like anomaly of SST in Nino 3.4, and something like that. And for pooled space and time, it is like a prediction map of surface relative humidity, something like that. Prediction map of isobar, prediction map of precipitation, something like that. And in spatial distribution, it is like hourly temperature forecast for Jakarta, is something like that. So based on data, we must identify uh, data type or kind of data that we will verify. After that, we must decide the verification method that appropriate with that data. Well, we move to standard verification method. The first is eyeball verification. In eyeball verification, we just analyze the pattern of data. We just compare uh, observation against the forecast data. For eyeball verification, the common data that we will analyze using this method is time series graph. In time series graph, we can identify the at least four elements. The first is time of maximum or minimum value. The second is data trend, tend to be higher or lower value. We can use the trend line to identify the second point about data trend. And the next, we must identify the differences of significant value. It is different with the first point about time of maximum and minimum value, because in some case, like let's say in rainfall, we will have the significant value and maximum value at the same graph. So we can ignore the significant value instead of just identify the maximum value. We must identify or we must analyze both of them. And then about time gap of significant values. It is there any time shifting about significant values or not? And the second type of data that can be verified using this method is spatial map. For spatial map, we can use three keys to know how good performance of the model. We can identify the intensity of signal, and then location of signal, is there any spatial shifting or not, and then about area coverage, is the model smaller or bigger uh, regarding or according the observation data. Well, dichotomous method. In some cases, forecast data is not only in continuous value but also dichotomous. In dichotomous method, data will be separated by a threshold into two groups. Yes for data that exceed the threshold, and no for data that doesn't exceed the threshold. In many cases, this dichotomous is used to verify existence of phenomena such as the existence of rain, fog, convective cloud, and etc. The first thing that has to be done if we use this method for verification process is we have to create a contingency table to see the frequency of yes and no categories of forecast data and observation. Combination of forecast data and observation in a contingency table is called a joint distribution. In joint distribution, we will have hit if forecast say yes and observation say yes also. We will have a miss if forecast no and observation say yes. Actually, it like explain that the model missed to identify the signal. And then we will have a false alarm if a forecast say yes, but actually in real condition there is no occurrence. And we will have a correct negative if both of forecast and observation say no, or there is no signal in forecast and there is no occurrence in real conditions. Total data of observed and forecast occurrence and non-occurrence in contingency table are called marginal distributions. For example, it can be used to verify the precipitation parameter. If we use the dichotomous method, we will have at least these verification parameters: accuracy, bias, POD, FAR, POFD, and TS. Accuracy is about how many fractions of forecast data are true correspond to observation data, and bias score, it is about frequency of forecast data say yes category compared to frequency of observation data say yes category also. And then POD is about how many fraction of event indicated by yes category that can be detected by forecast data. And false alarm ratio is about how many fractions of forecast data that say yes category but actually they didn't occur. And POFD is measure of data fractions saying no but cannot be detected by forecast data. And TS or threat score is about to know detection skills of yes event related to yes category of forecast data. Well, multi-category method. The verification method for multi-category forecast actually similar to the single category or general dichotomous forecast type as previously discussed or described. However, the forecast output, which then categorized into some value range, could make an ambiguity if measured by only dichotomous verification method. Thus, categorizing contingency table become a proper solution even if the skill score measurement quite similar to dichotomous verification. If we use the multi-category method, commonly we will use this following verification parameters. They are accuracy, Head skill score, Hansen and Kuiper's discriminant. Well, continuous method. In previous part, we have learned about how we assess the model's performance using categorical basis, and in this part we will assess the model's performance using its continuous value. In continuous method, the common verification parameters they often use is bias, MAE, or mean absolute error, and then MSE, mean square error, and then correlation. In every verification parameters has advantage or and disadvantage side. Bias for advantage side is helpful to identify the tendency of either under forecast or over forecast. And disadvantage, if we use this verification parameter, it causes the misleading of parameter values are so big or high. And for mean absolute error, the advantage is helpful to identify how far the forecast error is, and the disadvantage if we use this parameter is cannot identify the tendency of either underestimate or overestimate. And for mean square error, if we use this method, MSE is more sensitive to outlier error obtained from data corruption, anomalous event, and the other thing that cause the error. But if we use this parameter, we cannot identify the tendency of either underestimate or overestimate. It is the same with mean absolute error. And the last is correlation. It is Pearson correlation. If we use this parameter to assess the model or forecast performance, we can represent or we can identify the relation between forecast and observation data within overall the one dataset. But if we use only correlation, the disadvantage is we cannot identify how far the forecast error is. So based on advantage and disadvantage side, we cannot only use one verification parameter in a continuous method. We have to combine some of this verification parameter. Well, this is about the other method if we use or if we have continuous data and we use continuous method to verify this data. The first is histogram. For continuous or numerical forecast, the data distribution is noticeable. This forecast distribution shows its forecast characteristics, thus could be a comparison against observation data to obtain the distribution trend differences. The histograms is the most famous method to exhibit the distribution of the data, which shows in the left side in upper up left up corner histogram. From the figure of histogram, we notice that observation and forecast data show quite different data distribution. The observation distribution skewed to the left, while forecast or prediction data skewed to the right. It suggests that the model tend to overestimate when forecasting the temperature in Jakarta. Histogram shows a similarity between spread and skewness of forecast and observed distribution. The most important from the histogram there is this method solely exhibit general data distribution. Thus cannot represent a direct difference between forecast and observation data. In other words, the histogram is qualitative method which does not give the skill score information between forecast and observation. The next is scatter plot. This method is as simple as plotting the forecast value on the horizontal axis against observation value in or on the vertical or vice versa. The ordinate and the abscissa uh, the ordinate and the abscissa should have the same scale before doing scatter plot. The most skillful forecasts exhibit by those of scatter plot which with the most dot point clustered along the 45-degree line. In the other word, the forecast is being accurate when it generally has the closest gap of forecast distribution against the diagonal line on the scatter plot. And the next is box plot. Box plot has similar characteristic with histogram. They also draws forecast and observational data distribution. There are 5 statistical measurements that we could obtain from the box plot that are minimum value and Q1, Q2 or median, and Q3, and then maximum value. We must know or we must remember that minimum and maximum value actually not minimum real minimum value and maximum value, because in some data there has imbalance distribution. The real minimum value and maximum value become outlier data. So we must remember this part. Box plot can be used for understanding the distribution data characteristic. Despite to identify data dispersion degree determined by the length of box plot. It also can be used to measure the symmetric of the data dispersion. The length of the box implies both dispersion and variability observational data or forecast data, while the median position and whiskers length imply the symmetrical level. Well, we move to verification for probabilistic data. The probabilistic forecast or probabilistic data is a forecast type which not denotes the event magnitude or value or its existence directly, yet indicate the probability of the event to occur. The probabilistic forecast value is range from 0 to 1 or 0 to 100%. The probabilistic data can be verified using this following graph. The first is reliability diagram and the second is ROC diagram. The reliability diagram often or reliability often referred to as attribute diagram when the no resolution and no skill included in the diagram. In left side diagram or reliability diagram shows the reliability in or sample of reliability value which contain some bins, for example 0 to 5%, 5 to 15%, and 15 for to until 25%, and etc. So in reliability diagram consists of or build of some bins. The histogram of each bin also included in the sample histogram the perfect reliability, no skill, and no resolution line also plotted on the diagram. The reliability diagram uses observed relative frequency for the vertical axis and probability forecast for horizontal axis. The observed relative frequency and forecast probability distinguished into several categories or in k-bins. For example, in like I have mentioned before, 0 to 5, 5 to 15, and then 15 to 25, and etc. The forecast reliability denoted by the diagonal line in the diagram. The closer plotted pinned with the diagonal line, the smaller conditional bias the forecast. Furthermore, when the plotted point lying below the diagonal line, therefore the over forecasting is indicate or probability too high. When the plotted point lying above the diagonal line, indicating the under forecasting or probability too low. When the plotted point become flatter, it indicates that the forecast resolution become lower. It can be reason of the occurrence of horizontal line which showing no resolution condition where also denotes homogeneous forecast data within one data set as in climatological data. And the second graph or diagram is ROC or relative operating characteristic. ROC is a diagram that using heat rate or POD for the vertical axis and false alarm rate or POFD for horizontal axis. When speaking about POD or POFD, there must be a threshold that used for dividing the probabilistic forecast data into a categorical dataset. Or especially of yes and no categories. The probabilistic threshold determined according to its demand. For example, 0.05, 0.15, 0.25, or in percentage value. The area below the ROC graph usually used to seek the probabilistic forecast accuracy. When the ROC graph becomes closer to the upper corner of the diagram, it indicates that the forecast has a better scale. On the other hand, when the ROC graph becomes closer to diagonal line or even reach below the diagonal line, it indicates that forecast scale is getting better. In principle, ROC only represents the model performance to discriminate between two alternative outcomes. It can be said that ROC is technique for measuring the forecast category resolution. This suggests that forecast bias could not be identified by ROC. The reliability could not be drawn in the diagram as well also. The next method is common use in some research to assess the model performance is rank histogram, or often call it telegram diagram. This method is usually used to identify the ensemble spread of the forecast represent the true variability or uncertainty of the observation. This method is kind of histogram but use forecast data to create some bins or class interval. Observation data will be filled into those bins to know the spread of in ensemble forecast member. To construct a rank histogram, it is the following. It is the step how to build or how to construct a rank histogram. The first is rank the ensemble members from lowest to highest. For this example, let's say the model values of ensemble member are 0.2, 0.7, 1.4, 2.1, 4.2. And then we have to define bins based on the list of forecast value from step 1. There are 6 bins from this list data. The first bin is value below or lower than 0.2. It is the lowest value, and the second values between 0.2 until 0.7 and etc. until bin 6 value above or more than 4.2. It is the highest value. And the next step is place observation in the appropriate bin. Ideally, the large number of observations should be taken over multiple times from different locations. And then the next step is make a histogram using the new data. This histogram should be a uniform distribution since each bin should be represent an equally likely scenarios. The flat shape of this histogram, it indicates the ensemble spread about right to represent the forecast uncertainty. U-shape it indicates the ensemble spread too small, many observations falling outside the extreme of the ensemble. Dome or dome shape, it indicates that ensemble spread too large, most observation falling near center of ensemble. And then asymmetric shape or random ensemble contain bias. Okay, these are the other verification parameters if you want to verify the probabilistic data. They are Breyer score, or and Breyer skill score. For Breyer score, used for seeking the probability forecast errors by calculating the mean square probability errors. Breyer scores could be interpreted into three factors. They are reliability, resolution, and uncertainty. The Breyer score range from 0 to 1, where the closer to 0, the better forecast gain. Breyer score solely determined by event frequency. The more rare event, the easier it is to get a good Breyer score without having any real skill. And then the second one is Breyer skill score. Breyer skill score shows a probabilistic forecast skill relative to its climatology. Breyer skill score range from -infinity to 1. Zero value indicate that the forecast is poor of skill when compared to reference forecast. The closer value to 1, it indicates that the better forecast gain. Breyer skill score also shows the forecast probabilistic increment relative to forecast reference, usually for longer data series or climatological sample. However, Breyer skill score has an unstable value when applied for relative fewer data sets. Thus, the more sample data are demanded when Breyer skill score applied for a rare event. Now we are moving to method or verification method for spatial forecast, because we know that model actually never totally wrong. It just perhaps the model can identify the signal, but there are some spatial shifting. So it is important to use verification method for spatial forecast. The first, the one of some verification method that I want to share to you is intensity scale verification approach. Intensity scale verification approach is a verification method that represents a spatial scale forecast based on error forecast scale and intensity. This method commonly used for precipitation for verification or other variables that has a continuous dispersion. This is the sample of intensity scale verification graph or diagram or something like that. And based on this sample, we can identify how the model can recognize or can identify the signal based on threshold value, and then based on spatial scale. And what we also can identify what is the threshold that has the higher error, and what is the spatial scale that has higher error also, just using this graph or a diagram. Mean square error, or MSE, of the binary image is used to assess the forecast scale, as we know in this graph. The binary image itself, obtained from the forecast and analysis, separated into certain threshold of different precipitation rate intensity. It is just a sample. The scale score then decomposed on different spatial scale using the two-dimensional discrete wave-flat decompositions of binary error image. Therefore, the forecast scale can be evaluated both in terms of precipitation rate intensity or spatial scale. The intensity scale verification approach is further improvement of categorical binary verification approach. The previous method provides the information related to forecasting scale for different variable intensity, which then include forecast scale for various spatial scale as well. Okay, the next part is about still spatial term, or spatial type of verification method, but it is more focused in object of signal, or this method will focus on signal of variables that will be verified. It is object oriented method, and the one of object oriented method is entity based verification, or we can call it contiguous range areas in for example of this method. The object-oriented method verifies the spatial forecast from a signal or entity. This entity is variables from the NWP data defined by closed contour due to its discontinuous spatial value. Some examples of this entity are contiguous range area, or CRA, convective area, and low pressure minima. If this entity can be identified either as forecast or observation data, such as in CRA, hence verification can be attained by using pattern matching techniques to identify error over the area, mean and maximum intensity, and spatial pattern. The total errors that gain from verification can be divided into error based on location component, volume, and the pattern of its entity. This method is important for the NWP model development process. The entity which verified is classified as hits, miss, and so on, and false alarm, something like that. Based on how close forecast location from the observation and how well the maximum intensity is exhibited by forecast data. You can see in this sample of CRA approach, in the upper side, it is a map of observation and model data of rainfall or precipitation. In this image, we can see that there are some part that has the same value or identical value and pattern, but there are so many signals that mismatch between observation and model data. So we want to identify, we want to verify how many area that has match value, and if we want to identify the area, the first thing we have to decide the threshold. For example, we want to identify how many area, how many grids that has a value more than 20 millimeters, both in observation and model data, and we will get the map as we can see in lower side, in left side, intersection grid of more than 20 millimeters grid or 20 millimeters value. The red area is intersection grid that has same value, both observation and model. And if we change the threshold, we will get let's say we want to identify or we want to verify the model in value or in threshold in 50 millimeters, and we will get the second one, the map in lower side, in right side, intersection grid, and the red area becomes smaller than left side in 20 millimeters in threshold. Well, that's all for my presentation. I'm sorry if there are so many parts that we have skipped because of limited of time. But I want to say about this material, if that is actually model never say that model totally wrong, or we can say that model is not fundamentally wrong. They need to be interpreted correctly and communicated in a way that our customer understands. So using this verification technique, I hope we can interpret model better than before, and we can adjust the error, so we can make or produce better forecast information for public or our stakeholders. And please give me some question if you have some missing part of our material. Thank you.